good afternoon, everybody, or good morning, or good night. So today we have the pleasure here to have a talk by Professor Ney Calazans from Catholic University of the state of Rio Grande do Sul in Brazil, talking about asynchronous. And Professor João Leonardo Fragoso from State University of Rio Grande do Sul will be the session chair.
Thanks for the invitation. It will be a pleasure see a presentation of Ney, most in asynchronous circuits that we really love. So Ney was born in Maceió, Brazil. I can pass the date. And he received a bachelor degree in electrical engineering in 1985 and a master's degree from both from Federal University of Porto Alegre, and he holds a PhD degree in applied science mechatronics from the UCL in Louvain-la-Neuve, Belgium. It's in 1993. Since 1986, works at a School of Technology of the PUCRS in Porto Alegre, being a full professor since 1999. Follow a postdoc senior in USC in California. Actually, nowadays, his main research interests involve digital design in general, non-synchronous hardware design in particular. NOx, network on chips, computer architecture and application. Professor Calazans holds a research productive scholarship level 1C from CNPq, and is a EEE senior member. He's also member of SBC and SBB Micro, Brazilian societies, and has a lot of publications, really productive in research, and also advisor a great number of PhD and master dissertation theses. So today you talk about facilitating the use of asynchronous design from dedicated components to push button circuit synthesis. So you can see what is happening in asynchronous circuits today. Ney, if you please.
Okay. I'd like to thank first the invitation of CASS in the person of Ricardo Reis, and also for the kind presentation of João Fragoso. Both of them old friends from very long ago, and I'll talk today about asynchronous circuits, which is a subject that is not very new. Many of the old asynchronous circuits were used to build, for example, supercomputers in the past, since the 50s and 60s, and I'll just give some overview of the work that we have been taking on the last 15 years, right? So first a little bit of motivation. What's asynchronous circuits? Most of us know how asynchronous circuits work. We have a single clock that controls every storage element in my circuit, and I have combinational circuits in between. Yeah. Okay. Then there's some constraints, of course, are necessary when you do synchronous operation, and we have hold time and setup time constraints that constrain when inputs, data inputs can change before the clock edge occurs, or similar constraints can be found if I have not a clock edge based circuit, but level latch circuits, right? Then the setup time is the minimum time the inputs have to stabilize before the clock edge appears, and the hold time accordingly is the minimum time inputs must remain stable after the clock edge appears, right? Of course, another characteristic of synchronous circuits is that the clock must enter at every point, at every storage element, and so we can have a skew between the point where the clock enters the system and the longest point, the farthest point in my circuit. And this skew we have to control in synchronous circuits, right? The problem is wires are changing. We have here a graph that has been proposed in 2001 about the future of wires, the name of the paper. And wires are becoming progressively less fast, let's say slower, as the technology advances. Here we are on 7 nanometers, and we have huge problems. And the chip edge is slowly growing, which means that crossing a chip can take as much as 5 clock cycles or more today. Thus, how can we employ an overall synchronous design? Avoiding this problem is possible, it's always possible, but it's increasingly expensive. Besides, the clock distribution may take the 60 to 70% of the overall chip power, which means we have 40 to 30% only of the power budget left for the logic to employ. So this is a problem, of course. Of course, synchronous and asynchronous, comparing them, we have always a set of advantages. No wonder that we have still most people work on synchronous circuits or globally asynchronous, locally synchronous circuits. The initial design we can abstract. In the initial design, we can abstract entirely delays. Is one of the main advantages of synchronous design. The design is very easy to decompose as long as the interfaces respect the same clock. Hazard or glitches are very easy to deal with, and race problems are easily solved. Yeah. Also, there's a lot of Boolean and algebraic manipulations that we can do, and by ignoring the timing of the circuit, we can have this easily implemented. Well, the bad side of synchronous circuits is that the clock skew in very large chips is a design nightmare. So everyone that tried to finish a chip today has this problem of closing the timing of the chip if the chip is very large. They have a potential to waste energy because no matter if I want to use the clock or not, it's ticking all the time in every memory element. So I have a potential waste of energy. And the worst case performance is always the case because the longest path, combinational path that I follow from one memory storage element to the next is the one that dictates the longest path, or the slowest path is the one that dictates the performance of the whole circuit. Technology migration is a second nightmare because if I can migrate, if I want to migrate design from one generation to the next generation, all the problems of timing have to be addressed again. And this can be very difficult. Asynchronous circuits have the advantage of reducing this problem. The design is inadaptable to physical property variations, and it's very hard to take into account variations of process, voltage, temperature, IR drop, and other variations that occur in complex chips today. The metastability treatment in synchronous design is a third nightmare that all designers have to take care of it. And also the digital or analog integration is very hard. All of these could be seen as advantages of asynchronous circuits, right? So synchronous versus asynchronous, putting in short what we have. Synchronous design is a single method. Everybody learns how to deal with the synchronous template. It's well defined. It has ample support of EDA tools. Asynchronous is not one. Is a dozen or much more design methods or templates, logic templates that exist. We have to choose one, but we cannot know all of them, all of those that exist. So it's hard to learn asynchronous design because there are so many variations. Effective designs depend upon the model choices I make. I can make a choice on the delay model to use, a choice on the communication protocol to use, and so on. We will see this. And also, we can, in short, say that synchronous design is good, but it's reaching its limits. Support for asynchronous design, especially in very new technologies. Support for asynchronous design is missing a lot. So this is a problem for asynchronous. And the research community and the industry are trying to fill this gap. Right? So my presentation, given this motivation that is worth to deal with asynchronous design, I will try to show an introduction to asynchronous design, asynchronous circuit, in particular design, discuss some of the models and design templates. I'll try to go fast here because this is not the main point. The main point of my presentation are items 3 and 4, dedicated components for asynchronous circuit, and describe one method that we have developed over the years, which is the pulsar method, and a tool for asynchronous circuit design in a push-button way. Let's say I just give a system Verilog or VHDL description of my circuit in an RTL-like description, and I can push one. Okay, it's 3 buttons, not one, but I can make these 3 buttons in sequence, and have at the end a layout. I'll show you how we can do this today, right? And it's quite efficient. I can parameterize the cycle time of my circuit and so on, right? Let's see. So a brief introduction to asynchronous circuit design. Okay, we all know there are differences, but what's the fundamental difference between synchronous and asynchronous? Yeah, the main is the synchronization scheme. A synchronous circuit we can see in a very simplified way as a pipeline interconnecting memory storage elements and combinational logic between these storage elements, right? So, of course, we can have derivations and so on, but most circuits fall on in a simplified way in this characteristic, or most synchronous circuits. And the clock period is given by the longest path I have to follow, either in CL1, CL2, or CL3, the worst case behavior, right? In the synchronous circuits, we don't have this anymore. We don't have the single clock. We have local clocks that are generated using the handshake communication between each stage and the next using their storage elements. The synchronization is explicit, request and acknowledge handshake, local to each memory and combinational logic pair, which we call this a stage. We have no clock, and we don't have more a worst case. It's not very easy to define how fast this thing will work. We have to compute the cycle time, and this is quite complex to compute, much complex than in asynchronous circuit. Okay, before going further, we can examine a model for models. Let's say a meta model. Theoretical people like a lot of meta models, and this meta model has been proposed by Matheus Moreira in his PhD at PUCRS in 2016, which is a model of a generic digital circuit design template. And it's not only for asynchronous, but it's generic. So we can define a template of logic design as a template composed by a design style and a set of channels that interconnect, that are employed by this design style. A design style can be seen as supported by a set of cells and an architecture or how to compose these cells to form the implementation of my circuit. And the intercommunication within the architecture is given by a set of communication links and by a choice of protocols that implement the channel, right? So using this meta model, we can adapt any model of digital circuit design and see how we do synchronous design or asynchronous bundle data design, asynchronous QDI design, all these can be fit to this meta model. Let's see an example to illustrate the use of the meta model. We have synchronous circuit design. The design style is the synchronous RTL. There are IEEE standard that define what is a synchronous RTL model. So the design style is well defined. The set of components are Boolean gates that we have, for example, in libraries, or that we implement, or gate libraries for FPGAs. The architecture is interconnect gates forming combinational circuits, to do data transformation, interconnect functional module inputs, and outputs to registers. So we surround every combinational block with registers on input and output, and connect registers to input and outputs of the circuits. This is the essence of the register transfer level definition. This is the architecture that we use as design style together with Boolean gates. The channel on the other side is are the communication links that we use to interconnect gates, to interconnect pipeline stage wires that encode information as Boolean numbers. The clock controls everybody everywhere with a single signal. And the protocol, the synchronous one, when the clock ticks, every register or almost gets new data. Otherwise, nothing changes in the system. Between clocks, we are stabilizing the combinational paths that we have in our circuit, right? Okay, what does change when we go to asynchronous design? Almost nothing or everything. Almost nothing, we have a template, a synchronous template that is very similar to a synchronous design. If we modify everything, we can have a design template that get the most of asynchronous design, but it's very different, very difficult to understand, and very difficult to dominate before doing a design. The closer to synchronous, the easier to understand and to use synchronous to do asynchronous design. The farther we are from synchronous design, the better, because we can surmount the difficulties related to synchronous design. Well, power efficiency is always one thing that we advocate when we do asynchronous design. But this cannot be the case. There are some asynchronous circuits that are very power hungry, but they work very, very, very fast, much faster than synchronous implementations. You know, my colleague Peter Birrell from the USC once implemented such a circuit for Intel, and they have a circuit that has 300 watt power consumption at most, right? So, but it's very fast. Robustness to variations and single event effects are a problem with synchronous circuits and technology migration. We can enhance our capacity to be robust to variations, to stand single event effects, and even do almost automatic technology migration. The potential to age gracefully, let's say aging, it's much easier for synchronous that are asynchronous, for circuits that are asynchronous, because they also produce less electromagnetic interference. Okay, some examples of templates. For example, there is the work of Cortadella, published in ITCAD, Transactions on CAD, IEEE Transactions on CAD 2006, which is called desynchronization. The solution is very simple. We produce a synchronous circuit, synthesize it, and then using a set of templates at the physical synthesis step, we substitute the clock network, the clock tree, by local controllers that produce the clock for local master and slaves, master and slave slash. So I change the flip-flops, the edge-triggered flip-flops by master-slave flip-flops. These are done by manipulation on the logic description of the circuit after synthesis. And then I have controllers that are very clever, very small, because a local controller does not need to be a 100,000 states controller, as in a complex microprocessor implemented as a synchronous circuit. They can be very simple, 10, 5 states to control the way we command each and every latch in my circuit. And also I can do resynthesis, for example, migrating combinational logic to in between the master and slave latches and so on. And substitute the clock by a set of local handshake controllers, the controllers ears, and delay lines, right? Another example is a way that has been provided by the guys from Netherlands, Peters and others, published in Async 2010, so that we can use circuits implemented with conventional gates and flip-flops to implement asynchronous circuits using local controllers that are based on edge-triggered flip-flops and normal gates. So we don't have to implement special gates for manipulating asynchronous design, as we will see is our approach. Our approach is we develop libraries, and these libraries have special elements that allow us to manipulate information in asynchronous circuits much more easily than we do when we are using synchronous design, simple Boolean gates. Yeah. Okay. So to conclude this part, the Moreira metamodel is an approach to asynchronous design models and templates. It's a way of reasoning about the way we do design, especially when we use very many different templates and we want to compare them by means of formally compare them, which are the set, and decide what are the set of cells I have available, what's the architecture that I intend to use. So when the architecture is different for asynchronous design, it's normally synchronous, different from synchronous. Basically, always async templates and then employ another architecture, not the synchronous architecture. The set of cells can be the same as in the case of here and here. These two approaches employ Boolean gates. Well, this is not the case of Cortadella work because they use, in the controllers, they use some special gates, but they are very simple, small asynchronous gates, which are C elements. We'll see in a while. And communication links are distinct in asynchronous design. They divide async templates in two big template families. We can separate all the ways we have to implement asynchronous design in two big families of templates, the bundle data template and the DI or QDI templates. So two families of templates. The protocols are also different from async. Basically, all async templates employ a protocol that is distinct from the synchronous protocol because we do not have a global clock. We cannot simply wait for a clock in every storage element, right? Okay, let's see the second part of the presentation, yeah, where we have models and design templates. It's a little discussion on models and design templates. I promise to be very fast here, but we have to go anyway around some discussion. Okay. What we have here, the ordering of models presentation. Yeah. We will discuss a little bit about channels. Yeah. First, protocols with a bit of encoding, and then communication links. We'll discuss each of the 4 elements that define a digital circuit asynchronous template by protocol, and then communication links, and then talk a little bit about the set of cells that we'll discuss in more detail in section 3 of this presentation, and the architecture, asynchronous pipeline, flow specifications, and so on. So we'll discuss from right to left here. Okay. Let's go to the left, which is better. Asynchronous protocols, 4-phase, and single track. Yeah, I took these from the book of Peter Virel, published in 2010, about asynchronous VLSI design. Yeah, this is based on the picture in the Birrell's book. So we have here a 4-phase bundle data protocol. We have a sender and a receiver, request line, control line, and an acknowledge control line, and data that flows, right? So once I have my data ready, I put my data out of the sender, and I announce this by raising my request line. Then the receiver sees this, processes, and get the line saying, okay, I saw your request. I'll deal with them, with this request. And then in the third step, the sender say, okay, I can see that you are dealing with it. And in the fourth step, the receiver say, okay, I finished dealing with that, and I can change the data and start another round of the exchange of data, right? Okay, this is, we can see we do not need 4 phases, yeah? What about having a more economical phase protocol, which is the 4-phase delay-sensitive protocol, for example? Let's say the delay-sensitive protocol, I send the data, but I do not send the request because I embed the request together with the data. For example, by using a special encoding scheme, for example, the 1-of-n wires. I have 1-of-n wires to transmit one information. If I have n wires, I can transmit n distinct information using one hot code, for example. Yeah, but I can have no data by putting all lines of the data bus in 0, and as long as I raise one of the lines, I'm sending the data. Is this the first bit is the data 0, is the second wire is the data 1, and so on and so forth, right? And then the receiver notices this and knows and agrees with that encoding, detects that there is one line that went up, and announces, okay, I got it, right? And then this line can go low, and then I have again no data in the data communication. So one of the n wires rise, and -1 remains 0. This is not very economic, but it's simple, and I do not have to worry about the timing of the different wires because just one wire changes at a time, right? Another way is the single track protocol where I do not have at all a control signal. And I have a set of n amid the same encoding, n lines, and using a one hot code, but the lines are bidirectional. So the sender drives one of the wires high, and when ready, the receiver gets this data and sends the same line to low, and then things can start again. This is the single track. Just to show a little bit of the diversity of approaches that we have here. Okay, there are other approaches. I'll go very fast over this. And protocols, each of these protocols I showed can be narrow or early or late or broad, depending on where data is stable and where data is got. So I'll not talk much about this. You can take a look at the slides then after that. And the 2-phase protocols are another family of protocols where I do not have 4 phases to change data. I simply put some data here and change the request line to high to low or low to high. Each information here is a transition here means data is ready. The transition on the acknowledge line says, okay, I got it. And then I can repeat by lowering. Yeah. So 2-phase bundle data protocol, rising and falling transitions on request, new data is available. Rising and falling transitions on acknowledge, data was acknowledged. Sometimes this is called transition signing. It's the transition that is meaningful, not the sign-on level, right? Okay. Again, the one-of-n nature of some protocols, I'll not discuss this in detail, are variations, 1 of 2, 4-phase, 2 wires per bit, 4 wires, 2 bits, using an encoding that is not 1 of 2, but 1 of 4, and so on and so forth. Also, there are pull protocols where the receiver asks for the data, does not expect the request to get the data. So I just changed the request and acknowledge lines, going after that. So communication links, data encoding. How to represent information in asynchronous circuits? What are the options? The simplest one is to do as in synchronous circuits. 1 bit of information, 1 wire, Boolean encoding, as in digital synchronous circuits. But the lane sensitive is another idea, which I think is a very good choice, and we will work here mostly with the lane sensitive. The basic idea is to merge data validity, control, and data value in one single set of lines. The examples of DI code, 1 of 2, 1 bit, 2 wires. It's a special case of M of n, where I can have M of n wires in 1 is a valid code. M of n wires, I can have a combination of n wires, m by n. Distinct values represent, so it's a combinatorics here. And there are others, Berger codes, Knut codes, and often used codes are dual rail and 1/4. We'll basically use here dual rail, but we have circuits developed by 1/4. There's a very good paper available in the internet called The Lane Sensitive Codes, an overview by Tom Verhoeven, published on Distributed Compute in 1988, right? Go on, let's go. The dual rail concept is very simple. Yeah, let's say 0, 0 in 2 wires is no data. So I can represent the absence of data. 0, 1 is the 0-bit value. 1, 0 is the 1-bit value. 1, 1 is not used and is invalid. So with this encoding, that an inverter can be used by simply crossing 2 wires, because 0, 0 becomes 0, 0. So the inverted version of no data is no data, and the inversion of 0, 1 is 1, 0, just exchanging the wires. So I do not need hardware to perform inversions. Also, but if I go to logic gates like AND and OR, I need 2 more gates, 2 gates for implement an AND and 2 gates to implement an OR, because I have to deal with 4 signals of 2 values. A0 is the true line, A1 is the false line, A0 is the false line, A1 is the true line, according to this convention here. So the advantages and inconvenience. Okay, example of other DI codes. Yeah, I can have dual rail for 2 bits, which is this 0, 1, 0, 1, 1, 0, 1, 0, equivalent to the Boolean codes 0, 1, 2, and 3. I get the double of wires, the double of information stored. The value 0, 0 is an invalid code word that represents absence of data. All other 11 code words of 4 binary digits are invalid and unused. 1 of 4 is different, but takes exactly the same amount of wires to represent the same amount of things. Yeah, they have the advantage that between one code to the other, or from one code to null, I have just one transition, while here I have 2 transitions to go to 0 again or to another code. So this is power saving code. There are others like 3 of 5. Yeah, the code 3 of 5, 3 ones of 5. I have more valid codes, but also I have a lot of code words for binary digits which are not valid. How many bits of a 3 of 5 code can represent? 2.5? I don't know. It's more than 2, but less than 3. Okay, right. I'll save this for later. Channel and template families. The main delay wire, main delay models. We can have gate delay model where delays are only at the output of gates. I can have a wire delay model, which is more powerful and more used today, but more complex to deal with. Each wire has a delay. Yeah. Going on, let's see. Based on these choices, the choices of taxonomy, the taxonomy based on choices of protocols and based on codes. Yeah, I have bounded delays, which are bounded delay model, which is very realistic for gate or wires, and technology mapping is easy, verification is difficult. This is the most similar design template to synchronous design template. So it's very similar. The bundled data circuits are very similar to synchronous. So the design is very similar. The lane sensitive is not very useful because it's a limited class of designs. Speed independent is kind of do what you can as asynchronous design. It's more an engineering way of dealing with a specific circuit that I have to produce. And QDI is the lane sensitive except for critical wire forks called isochronic forks. I won't talk much about this. Yeah, in practice, it's the same as speed independent, right? Okay, so components that we use. We talked about protocols. We talked about encodings. Now let's talk a little bit about components. Special components may be interesting to use while doing asynchronous design. And maybe the most interesting component is the C element. The C element is a component that has this truth table. It is a sequential element because inputs, both inputs in 0 for a 2-input C element, set the output to 0. Both inputs in 1 set the output to 1. And distinct inputs, distinct input values, the gate keeps its previous values. The implementations can be seen here. One implementation with 8 transistors, one with and 2 with 12 transistors. This one is economic in terms of area, but wastes more power because we have to fight these 2 inverters. We have to fight with these 2 inverters to set a new value to the output. So we have short circuit current that it can be very high. These implementations here spend 2 more transistors, but they are I'm not managing to advance the slides. Is there a problem here? Maybe someone can help. The presentation is not going to the next slide.
It's strange.
Okay.
Now it's okay.
Okay, it's okay. So next, what we have here, there's a family of asynchronous gates that we can employ called NCL gates. What are NCL gates? C elements are a special case of NCL gates, which are threshold gates. We have a threshold function, but plus hysteresis behavior. Inputs have weights, and if the sum of all product of the weights by the inputs is larger than the threshold, then the output goes to 1. For example, I have here an example gate here, where I have a threshold of 2 and 3 inputs. If 2 of these 3 inputs are 1, the output is 1. If less than 3 inputs are 1, I depend. If all are 0, then output is 0. And if less than 2 are 1, the output keeps its previous value. So we have this set of elements. We can have many gates, and depending on the weights, we have many possible implementations of these gates. These are the libraries we employ here are based on this kind of gates, right? Okay, yeah, and We don't need to go to other components. There are mutex, or there are several kinds of implementations. I'll go very fast to this. Let's see a little bit about how does a circuit works. Yeah. So let's show a circuit, an asynchronous circuit's working. And the simplest possible asynchronous circuit is a Muller pipeline. A Muller pipeline is comprised by C elements interconnected with other C elements and other C elements and so on, an environment based on an environment that produces requests, a C element that is able to fulfill this request by making the request go ahead to the other stages, and an acknowledgement which is produced by the output of the C elements to the environment. The next stage responds to the previous stage and ahead. So we have the delay-sensitive handshake machine. Ci accepts 1 or 0 for Ci minus 1 only if Ci plus 1 is 0 or 1. So if accepts 1, if the Ci plus 1 is 0, if the next stage can accept new data. Think of 1, 0, 1, 0, 1, 0 as waves of values, 1, 0, 1, 0. C elements propagate waves precisely, and the timing depends on local delays, which may vary along the pipe. If the environment, the receiver environment is quiet, the pipe will stall, and the first data will stop here, and then the next data will stop here, next data will stop here, next data will stop here, and then the environment will not be allowed to add more requests because the requests will be blocked by the C element. The same is true for two-phase communications, and it's symmetric, same right to left, like electrons and holes, and this is the C element truth table, right? Okay, we can add to this basic control pipeline, we can add latches, and then we have an asynchronous FIFO with 3 latches, and the latches are controlled. They are transparent or blocking or opaque, depending on the C element. And I can also have functional blocks and delays, matching delays added here. This is a bundle data implementation, very similar to a synchronous circuit where the clock was changed by this very simple control logic here, right? So I have 2 gates controlling the generation of the enable for this latch. I have a delay which is matched to the functional block delay, so that the request does not come before the function block has data ready on its output, and the latch is ready to capture this data, right? I can have 2-phase bundle data. I can have also, which are known as micro pipelines. I can have 4-phase dual rail, the original Muller pipeline. Okay, let's go. 4-phase bundle data pipelines look like a synchronous pipeline with local clocks. When full, the C elements outputs are this scheme here, this encoding here. Only half of the latches store data, because one latch that stores data avoids that the previous latch store data too. So one latch is holding data while the previous one is empty. And only when this data of the first stage goes away, I can follow the new data to the first stage, and then I'm ready to capture another data. So it's what we call a half buffer, because only half of the buffers have useful data. This seems a waste of hardware, but it's very fast. That's why, because asynchronous pipeline can be much, much faster than synchronous pipeline with half the state. Yeah, like master-slave flip-flops. Important, half buffer pipes with feedback. For example, if I do a ring to make a counter, for example, I must have at least 3 stages to avoid deadlock. So for deadlock freedom, we need at 3 states or more, because I can either have empty data and empty, or I can have data, empty, data. Okay. Two-phase bundle data uses transition signaling. Yeah, this is another possibility. And let's go to, there's a capture pass transition, which is a special implementation of micropipelines that was proposed in the past. I'll not go long on this. The Muller Pipeline, again, with completion detection and using dual rail encoding of data. And also two input data. I'm not keep much time on this. Now that we have the asynchronous templates designed or studied, we have either we use Boolean encoding of data, or dual rail, or 104, or any other delay-sensitive code to create the QDI circuits. Yeah, I have protocols, two-phase, four-phase protocols, or bidirectional, and other combinations of protocols. Now, I'm going to pass to the first part of the presentation, where we want to talk about dedicated components for asynchronous circuit design and how to provide support to do asynchronous QDI design, right? Let's see. Okay. I'll pass this. Maybe we can come back to this. But let's see. We have proposed. No, we have to go back here. Let's see. Our research on asynchronous circuits, there's a mistake there, it's asynchronous, started in 2006 with trying to adapt to the use of asynchronous circuits over FPGAs. This is not very practical. We developed some works on Gauss interface, networks on chip, asynchronous and Gauss networks on chip, Gauss systems, secure hardware. Together with the LIRM laboratory in Montpellier, France, we developed some very interesting works around the years 2006, 2010. And then we said, okay, we have to go to ASICs to take advantage of asynchronous advantages. So between the years 2010 2012, we decided to do some studies on what asynchronous circuits cells, the cells of a library that we use. I intended to use a library that was available to design asynchronous circuits. There was none at all. So we had to create libraries, create cells, study the problem of cells in this period: area, power, delay, robustness. How do I organize the implementation of cells, of gates that I use in asynchronous design? So the first Asyn QDI library, Asyn means asynchronous standard cells enabling and designs. This is the name of our libraries. QDI library. The first one was developed for the ST microelectronics 65 nanometer, a set of a bunch of NCL gates, tools to support asynchronous cells design. We developed a method for sizing standard cell standard cells for asynchronous design using ring oscillator generators and cell specifiers, which were tools we implemented, CAD tools to implement this. And we also developed a special method to do the characterization, the physical characterization of asynchronous standard cells, because at the time, the cadence tools or synopsis tools could not characterize correctly the tools, the cells with asynchronous circuit feedback, because they only could be dealing with special templates like latches and flip-flops used in asynchronous design. NC elements and NCL gates were not like that. So we had to develop a special approach in EDA for characterization of the cells. So the Asyn A flow that I'll describe next. And the first paper we published in Async was about some cooperation we had with the guys of Leti for producing robust networks on chip in France and in Porto Alegre based on the network on chip they have designed. We developed robust NOCs using an encoding, using a 3 of 5 code for QDI implementations. So between the years 2010 2016, we worked with the RTO protocol because usually NCL gates employ the return to zero protocol. First, I change one input, and then I go all inputs to zero, return to zero protocol. And we created the return to one protocol and NCL plus gates, which are gates that employ another protocol different from the RTZ protocol of NCL gates. We created another kind of gates. And based on this, we finally developed the basis of our method, which is the STD and NCL QDI template. Talk about this later. We work with the guys from the University of Southern California, 2014, 2015, and later on bundle data design. We created bundle data NOCs. We create bundle data processors implemented with the Blade template that we patented together with the guys from USC. This was patented method, and now there's an enterprise that was created to commercialize solutions based on this method. We also developed a new C-element topology different from the 3 ones I showed before. We created a new reconfigurable delay element. We studied metastability, and we created with the guys from USC and from the Blendix enterprise in US testable mutexes. We developed a method to recharacterize cell libraries, and this method was furnished by demand to Qualcomm, and Qualcomm uses the method we developed here in Porto Alegre to recharacterize cell libraries in their foundry. We dominate the AC prototyping. So during these years, we prototyped 2 system-on-chip SoCs containing a processor and in TSMC 180 nanometer technology, and we implemented by the time only synchronous circuits should dominate the technology. Yeah, we create also. There are people working on the testing of bundle data circuits. Today there is a guy that made a PhD in our group, and now is working on in Germany on the IHP on the design of asynchronous circuits testing on the IHP foundry. We also organized the Async 2016 in Porto Alegre. First time this conference occurred on the Southern Hemisphere, right? Okay, between 2016 and 2020, that we'll explore here in this presentation in more detail, we have what we call the full circle of asynchronous design. Okay, a push-button method to design asynchronous circuits. We created new Asyn QDI libraries in FreePDK45, TSMC 180 nominal, and TSMC 180 near threshold, and IHP 130 nanometers. But the 2 last ones, the 3 last ones libraries are still under development. Okay, the first in-house patent that we developed is called Velo. It's a template for ultra-low power asynchronous design, and the near threshold library that we developed is the development to support this patented technology. Also, we created Pulsar, which is a tool for push-button tool for QDI circuits. Also, we implemented an asynchronous QDI RISC-V. It's under development. It's not ready. And we have the first SoC IC prototype, which is now under taping out by TSMC, containing a RISC-V synchronous and some asynchronous module communicated with the asynchronous design. These are more or less the overview of all that we have done in asynchronous design in the last 15 years, right? Okay, so one of the, you have seen here, one of the interesting things that we have done is to develop libraries to enable us to design asynchronous circuits. So the Asyn math design flow was developed with some help from Federal University. For example, Adriel Zimmer developed the part of the cell layout approach that we adapted to our flow, and others participated in the circuit design phase that I'll talk later on the SDDS template, right? Okay, the Asyn design flow is a flow for designing cell libraries. So we have a basic template. This basic template is defined how the library will be, for example, compatible, for example, with a library from ARM, or compatible with the ST Microelectronics library, or compatible with the TSMC library, so that we can use all the gates in the commercial library and mix in the design. We don't have to design inverters. We use from the commercial library, yeah? And we use our special gates to design asynchronous circuits. We have a cell sizing approach, the cell layout, and cell characterization, traditional. I'm not spending much time on that. So the library templates, the phase of the library templates uses our RowGen file generations and our tools that do the sizing. Yeah. Also, there is the RowGen tool and the cell specifier tool that chooses the best dimensions, and the RowGen does exhaustive simulation on the sizing of cells, and the CASS helps us choose the sizing, the adequate sizing of the cell. Okay. Using the Astran, a tool developed in the Federal University of Rio Grande do Sul that we adapted to our flow, described it in these publications here. We have some publications together on this use of Astran for asynchronous design. We also extended the cell characterization using our Liken tool, an in-house tool. And finally, what can be done with Asyn? Develop ordinary cells, inverted NANDs, etc. But if I have a library that is compatible with a standard cell library, I do not need to design them. Develop sequential ordinary cells like flip-flops, create sequential no-conventional cells. This is what we want. Care of dimensioning C elements, NCL gates, etc. Liken, enable characterizing all above. Create cell libraries compatible with existing ones, and several libraries, the circuits are built with this. Right. Okay. Today, RowGen and CASS are less used. They are being substituted for some heuristic sizing, and we are now developing a new approach for developing a sizing tool that is more flexible than this approach. Also, we have the Liken has been abandoned because the new Cadence software, since the Liberate software was we were able to use it, it was do the work of Liken and much more. And the Astran has been substituted by the Silvaco Cello layout generation in an accord and an agreement that we have with the guys from Silvaco. We are using them for using professional tool for designing the layout of the cells and semi-automated process of cell layout generation. Okay, the first Asyn library was released in 2011. It had 508 standard cells, 400 NCL elements or NCL gates, 4 metastability filters. Yeah. Today, we have more than 1,000 gates, NCL, NCL plus, inverted NCL and inverted NCL plus. We have set control, set reset no control cells. So we have several topologies. We have mutexes elements. A total of 573 cells are ready for use out of the 1,080 that have been partially designed today. Okay, also we have FreePDK that is available on GitHub. You can access the GitHub FreePDK 45 Ascent, where we have 159 cells for designing NCL gates, NCL and STDS NCL. More than 30 cells of each in 3 drives, characterized in 3 corners: nominal, slow, and fast, still under development, but it's already available release of this library. Okay. What is slide 55? I don't know. We have some ongoing work on libraries, 3 libraries on ongoing work. Okay, let's go to the method. Pulsar method, it's a method that and tool for asynchronous circuit design. Okay, right. All started in SBCCI 12 paper that we published, where all NCL gates are positive unate. Assume RTZ. What about negative unate and RTO? So we verified in that paper that we could have savings on, at least on static power, using this kind of gates. These are the results: almost 50% or more power saving, static power saving, based on they use just changing the way. And follow this. What if we mix RTZ, NCL cells, and RTO, NCL plus cells in a single circuit? A new logic template resulted, which we call a spatially distributed dual spacer, or STDS. Combined with NCL and NCL plus, we have an STDS NCL that enables us fully synthesis tools. Cadence Guinness or Synopsys DC synthesize STDS NCL almost correctly. They made the little mistakes, but these errors can be corrected by a linear time algorithm we developed called fixed XNetlist. An Async 14 paper explains the theory here, which is a little bit convoluted for logic. And we have, again, a cooperation with the guys from Federal University, Professor Ribas, Renato Ribas, Professor André Reis, and Myler Martins, and André Neusling Silva. We published this paper in Async 2014. We created this a new design flow, which evolved in other papers that we developed during the years 14 to 18, right? So this is the flow using commercial tools to design asynchronous circuits. Right, let's go forward. The new STDS flow, we are on the path to push button asynchronous circuit synthesis, but we are not yet there. A theorem that we proved on the IEEE Transactions on Circuits and Systems 1 in 2018 shows that approach works. Also, the Asyn libraries and virtual libraries that we had to develop that fool the commercial tools, and the fixed XNetlist and extensive scripting guarantee that we can do things almost automatically. Basically, a logic, tech map, and physical synthesis approach is guaranteed, but the input is that at first was at the schematic level. So we are limited to combinational circuits also. So more work was required. Yeah. So here we see a half adder, and this half adder described in Verilog is transformed in the set of gates, which are not STDS and CL. These gates are mapped into gates to fool the commercial tool, and then the fixed netlist corrects it to STDS NCL, NCL plus, NCL, NCL plus in this order. And then the circuit works and can be implemented to the layout level with the physical synthesis step, right? Okay, we're almost at the end. The real push button STDS NCL solution was proposed in last year in a synchronous conference, yeah. And the main problem to address, we had no defined temporal barriers in Async. What we did, we create abstract models of flops and latches based on previous proposal in Async 12. We enhanced this proposal with dummy clocks, and we have flop models and new latch models that we use to say, okay, this NCL gate is a flop or is a latch with a clock, but the clock does not exist. They are dummy. And we fool the tool. The tool uses the clock, creates the clock, and even computes for us the cycle time of our asynchronous circuit. So it's desirable to compute cycle time. We created a new model, which is a PetriNet model-based model. Here we have an example, an instance of this model to compute the cycle of every combinational path that we have in our pipelines. And the sequential nested NCL flow is the one that shows us how this works. Okay, but still there was some things missing. The main problem we did not have a front end. So we published in 2020, this year, the Synchronous conference, the design of a front end. Now we have Pulsar front end that accepts RTL like Verilog, System Verilog, or VHDL inputs, uses commercial tools to do the synthesis, creates a graph that will be expanded to dual rail implementations. These dual rail implementations is the output of our tool. We have a tool to, based on the HBCN model, half buffer channel network model, can compute cycle time, generate design constraints for the flow that we defined in the previous paper. So this flow here is the STDS NCL design flow. Act generation was walkered, we changed this, and HBCN was manually computed, now it's automatic. So now we have a complete flow for the asynchronous design, right? Okay, some results. So here we have some results where we compared our flow, that we can see that we have better, this is the results for implementations of multiply accumulate module of 32-bit, 16-bit inputs, 32-bit outputs for 3-stage, 4-stage, 5-stage, and 6-stage. And we can see we get better results than a baseline implementation in NCL. Compared to our STDS NCL, we can control much better the area, reduce the area more, depending on the number of pipeline stages and depending on the constraint on cycle time in nanoseconds. Okay. Also, we have better results in terms of achieving the best slack, the zero slack, and whenever we have a mean cycle time, we can get better results. Let's say red dots are negative slacks, the places where we have cycle time violation, that we cannot use the results, and we have less results with cycle time violations than in the baseline. And also, the amount of energy per operation is much more reduced in our implementations. These are STD Pulsar F implementations. These are the baseline, the first one, right? Okay. These are some layouts we generated automatically, or almost automatically. We have 3 steps I can show you. The 5-stage MAC, the layout implementation on FreePDK 45. A 2-phase dual rail encoded 8-stage asynchronous FIFO, layout automatically generated with 3 steps. And the chip we are fabricating right now, this is the MAC multiply accumulate module. This is another small module. It's a delay line for bundled data asynchronous circuits. This is an implementation of RISC-V and a ROM memory and a RAM memory inside that. RISC-V core, ROM, and peripherals for input. We are waiting for this chip to arrive so that we can test it, right? Okay, what lies ahead? I don't know if I have time for do a small demo, but I would leave some 5 minutes to show a demo of our tools working. Can I afford to have these 5 minutes?
Yeah, please.
Okay, so let's go. I'll share my screen. No, I'll share this screen. Okay. Probably you are seeing my screen here. Let me just exchange for the screen, and let's launch here my connection to my server back in PUCRS. Cut my webcam, and let's see. You're seeing just my screen, right? Okay. Connect. Connecting. Just a minute. Okay, I'm connecting to my server at PUCRS. Okay, I'm there. All right. So first, this is the description, RTL description of our asynchronous Mach 5 stages. I'll not spend much time here because there's a whole way. I said it's an RTL-like. You can see this is a system Verilog implementation, and it's possible to deduct that this is a 5-stage implementation of the Mach Ethernet. Here's the multiplication and accumulation step, and we have 5 stages here. Okay, let's see if I can. So we are here on the RTL. If I see what we have in the RTL folder, I have 2 implementations, the Mach 5 system Verilog, and I can run my implementation. Just a minute. As the first step is synthesize RTL, syn RTL using Pulsar for the Mach 5. So the synthesis, I'm launching our tool. It will take less than 2 minutes for this circuit. Meanwhile, it will create a folder with the output here. This is a large server, 24-core server running Linux. And we can see it's creating. Okay, if we take a look at the output, the Mach 5, the RTL is still empty. Within some minutes, it will start launching here in this folder the files that describe the logic synthesis results. Calculating the cost. I'm running Genus tools, which is Cadence Genus tools. Okay, it's taking a little longer. Yesterday was 2 minutes, but maybe there's more people using the tool. Right.
Yeah.
Okay.
Demos should not work.
Okay. Sorry?
No, just joking. Go ahead.
No, it works. So I have some report here, and the first report, RTL timing. Yeah. Won't have time. The slack is data path. I have the slack. There's not much, and the gates, the amount of gates that I used to implement. So this is still logic synthesis. The synthesis that still have to go by to path a step for producing the logic gates. So here we have the virtual gates that are gates of a library, a virtual library, that will be converted to our NCL gates by the next step. So I'll launch the next step. which is the syn STDS to map to STDS. I choose the library, FreePDK45. The name of the module, oh, it's not this one. The module is the Mach5. I have to change this, Mach5. Oops, sorry. And I have a constraint of 6 nanoseconds for the implementation. Okay, it's running. 2 more minutes. It's creating this FreePDK with a target 6 nanoseconds of delay. This is the constraints that we use. It's not yet filled. But this is the synthesis step, the synthesis step, the technology mapping step that will map our virtual gates to the effective gates of the library. Then I just have to pass for a script that will run that will produce the layout. I'll not have the time to run this because it's takes longer and a few steps, but we do have a script that do this. Okay. Let's see. Few more minutes, maybe 1 more minute will be ending. Okay, replacing gates. You see the names of the NCL gates here, NCLP, NCL gates, which is replacing the gates in the netlist by effective gates of the library. Okay, it's creating the files here. Power report, timing report, worst case report, and we can take a look at them right now. It's finishing. Okay, finished. So the technology mapping and physical synthesis is almost ready, but not the layout. So we are just missing the layout. There will not have the time to see this. We can see the, let's see. We have 3 corners: best corner, the worst corner, and the best nominal and worst corner analysis. We have SDC constraints, and the snapshot contains the data that we use to run the scripts and generate the layout, right? So one thing that we can see here is that the layout generated by, let me go back here to the implementation. Show this, stop. I have to stop my, sorry. I have to stop my sharing. Here. Okay, so what lies ahead? We still have some steps to go. One of the steps is to create special components that we use for the synchronous, asynchronous design. For example, using mutexes and using pipelines which are more complex, and avoiding consumption of tokens in my pipeline requires new components. These components have been developed. We are still implementing them, and they do not necessarily need new cells, but they are components that will be used during the synthesis of our circuit. And we're still developing this, and we still have to address, for example, more advanced implementation nodes, let's say FDSOI, FinFET, but basically we already have a set of libraries that support the building of asynchronous design using a push-button-like process. So I'm done here. I'm available for questions. I don't know if we have a question and answer session, but I'm available for this.
We thank you, Ney, for the presentation. We have a question. If you can talk a little bit how you can simulate this asynchronous IC design and search for flaws or errors on that.
Okay.
And you add some specific information. You take a synchronous design, a synchronous description, synchronous-like description, and you synthesize it, and after you move that to a do-array circuit. And
okay.
My question is why you care about timing, clock timing, in the first design, because the idea is kill the clock after that. And second, for example, if you have how you work when you have, for example, 2 clock domains, and you cross a signal from one to another. Most of the time you use a synchronous handshake to do that. So you catch this information because you already had the asynchronous handshake there. So you don't need to expand. I believe that you don't need to expand everything in both sides because the handshake is already there. You have a bundle data between request and acknowledge. You think you maybe I'm just wondering if your approach will not add more stuff that you need, because you are treating one clock design and another one clock design, and when you put together, maybe you don't need everything that you put in both designs.
Okay, let's go one question at a time. I can see the question of Clovis here. Would it be possible for you to talk a little bit about the simulation of the async CI's design? Talk a bit about simulation. What we do when we do the synthesis, we generate SDC files, but we also generate the timing of the circuit, SDF files for simulation, and we can simulate these files. When we do at the logic level, we want to do the simulation, we use the models I presented before on the beginning of the talk about STTS and cell. We have some models, abstract models of flop and latches that are put in place of NCL gates that work like registers. And so we can provide to synchronous simulators this model with these latches that we model abstractly, because they have a clock. And the clock is generated just to do the simulation using the timing information of the physical or logic synthesis. So we can simulate the asynchronous design effectively, right? Second, so we have a clock, but this clock is dummy. It's a dummy signal, just use it to enable the simulation. And we use a latch model with an enable clock so that we can provide the simulation. There are lots of techniques involved, but basically is that we use an abstract kind of component, and this component can enable the implementation of the running of the simulation of the asynchronous circuit. Okay. The second question, I think, was about how to cross domains when we have an asynchronous. Okay, if you have 2 asynchronous circuits, we do not have to cross domains because you do not have clocks. When you have a synchronous circuit and an asynchronous circuit, they have to talk. And to provide communication, we have to use special circuits that are synchronizers or filters that to avoid metastability. We have these companies already designed, and they are inside our tool. The tool can do with that and can do the synchronization with a clock, external clock of a circuit, because our tool provides the synthesis of a synchronous design, asynchronous interface, or between two synchronous interface. We can put the design, we can do the design with our method. For example, you can design an asynchronous FIFO using dual rail encoding without using clocks at all to adapt to synchronous domains. Okay. There's another question here that I see. The layout synthesis you have also done for FDSOI and FinFETs? No, I have. This is future work. We want to do work. We already have some predictive technology for FinFETs, and we have access to FDSOI of ST microelectronics 28 nanometers. But we have a very serious problem in generating cells for FDSOI 28 nanometers. So the layout generation is a complex problem. Even Silvaco tools that we use today are not able to generate the layout for us for FDSOI. So this is still we have a problem. Also, and for FinFETs, we could work with predictive technology at 15 nanometers, but we have not addressed it yet. There's also a question by Jean Dallolio. Are these spin-offs? Are there spin-offs and startups working on async design? Definitely. Take a look at a startup called Chronostack. I'm putting here. The Chronostack is an enterprise that absorbed two of my previous students, and they are doing very serious work on asynchronous design. What's their specialty? Their specialty is a startup specialized in creating asynchronous interconnect for very large chips, and created a method based on 104 communication, QDI communication, for interconnecting thousands or hundreds of cores inside a very complex IC. They were doing a tape out in 5 nanometer TSMC of a very large chip. I don't know for whom was the chip, but I know it's for some big company, because who does 5 nanometer layout today? I know it's not Apple. There is Qualcomm, NVIDIA. There are not many enterprises doing 5 nanometers tape outs today. So this enterprise hired Chronostack to do their interconnection, all the interconnection inside the chip, using the technology they developed. And two of the guys that work there, one of them is the technical director of the startup, is the technical director of Chronostack, which is called Mateus, my ex PhD student. And there's also another student, Mateus Gibeluca, which is working with him in this enterprise that is located in the San Diego, California. Right? There are other. There's an enterprise in Washington, state of Washington, that acquired the RAM. There was the startup I mentioned before, RAM, was bought by an enterprise called, how do you say, the guy that, oh, I never remember the name of the enterprise. It's an enterprise that deal with security circuits. And they acquired RAM, which was a startup created by the time I was in California to commercialize the bundle data approach developed by USC and our university, my students, and Peter Burrell's students. And I don't remember the name of the startup, but it's very easy. If you see who acquired RAM, you'll see which startup is this. This is not a startup that acquired RAM. It's a bigger enterprise. Any other questions? Yeah, my opinion, the reason why you have more works and tools that work on asynchronous design is because the demand is greater in this area, or some other more specific reason, perhaps a greater difficulty in work on asynchronous design. Well, yeah, the problem, the basic problem today, there are two basic problems, right? One, almost nobody knows how to do asynchronous design, so education is a problem. Two, the tools do not work well. The synchronous tools of Cadence, Synopsys, and other tools do not work with asynchronous design. They cannot deal with that. That's what we are doing, trying to create people that is trained in asynchronous design and develop a method that can use commercial designs that are very powerful to do asynchronous design for us, doing what the commercial tool cannot do, right? So these are the two base problems. But of course, most of the implementations do not need asynchronous design. Synchronous design is very fine. It's great. It's perfect for most of the tasks. But sometimes, yeah, asynchronous design can be the difference in some niches. There are some places where asynchronous design is a must. Security circuits. So the best way to resist to side channel attacks is using asynchronous design. Okay? What else? Complex communication inside complex chips. The best way to go is asynchronous. The guys from Leti in France developed that. 3D communication, 3D chips. Communication in 3D chips is a mess. If you have clocks, how do you cross a clock from one layer of the other on a 3D chip? This is not easy. It's very complicated. Yeah, asynchronous is easier to do. So I see at least these two great fields: security circuits, yeah, resistant, robust circuits for security. For example, also for space applications, where you have single upsets all the time, asynchronous circuits can do better with that. Yeah, and communication circuits, or communication inside complex circuits. Right? I don't know if I answered the question of José. Any other question?
Well, just a final question. When you talk about dual array, you have the initialization problem, no? That must initialize the pipeline correctly to allow the data flowing. How will you infer that from the RTL code? Which ones should be initialized or not to start the pipeline? For example, if it comes from a synchronous pipeline.
This is one of the things that are built inside our tool that can deal with the way you describe your code. It's not any code, RTL code, that we can transform into a synchronous circuit. So you have to use an RTL-like description. You can use System Verilog, VHDL, or Verilog, but you have to, sometimes we have to, by hand, insert some special components that are recognized by our tool. So we have hold components to avoid that a communication always takes place, that a handshake always takes place. We can avoid a handshake. We can initialize using special components. So we have special components that we insert, and we put, like I was putting a special module inside some design. Those that already worked with FPGAs know what I'm talking about. You can instantiate block RAMs inside your design, and these block RAMs are not basic VHDL, but they are recognized by some library that you load from the vendor, the FPGA vendor, that you can put their code inside your RTL code, instantiate here a block RAM or a multiplier, hard-coded multiplier. The same approach we use in our tool. You put some.
Okay, and the commercial tool can handle that without problem, or just attributes that you put there, or you black box some modules to the
you say to the commercial tool to ignore that, or to pass that on to the synthesis result that will be dealt with by our tool later, our scripts later.
Okay.
So that's the way we go. We put special components. So you have to learn something about asynchronous.
Yeah.
Something you have to learn. How and when to use these basic components, and what you cannot do that you can do in regular RTL. You can some parts you cannot do.
Yeah.
I still trying to make my students prepare a manual about our subset of RTL. And that's hard.
Yeah, but we should learn people to deal asynchronous.
Yeah, I have a very great PhD students now working on this. Marco Sartori, Tassiano Rodolfo, they are very good guys working on that, and they are doing a very good job in implementing. Mostly, Marco Sartori was the guy that enabled us to do synchronous asynchronous sequential circuits work. And he's a very good guy in programming, lots of skills on programming skills in Haskell, C++, and so on, right? And also, the tool is available. I didn't mention that, but the tool is available at GitHub. You can download and use it. But of course, we need access to Cadence tools to run the logic synthesis and the physical synthesis. But if you have this, you can download our tool and run just as I did here.
There is a final question by Professor Altamiro Suzin.
Oh, yeah. Hi, Professor Suzin. Great. Nice presentation. Congratulations. What do you expect for your RISC-V, considering area, power, and performance? Well, I expect I can get some money to make this huge circuit to be prototyped. This is what I expect, because it's going to be huge, right? I showed you in the presentation the size of the Mach-V layout. It's half the size of an entire synchronous RISC-V in the same technology. So, but I think we can make some optimizations, especially if we go to the near threshold version of our library, the SMC library that we are implementing right now. I can expect to reduce at least 40% the area of the asynchronous QDI circuit by giving up of some of the robustness of the logic. We can reduce the voltage scaling, and run in 180 nanometer with very less area, let's say 60% of the area of the RISC-V. But we are still finishing the logic implementation of our RISC-V, and the RISC-V case study is a case study that we are using to ameliorate, make our tools better. So we are doing chip design at the same time as EDA development. So the RISC-V implementation is being used to enhance PUCRS tool. And the PUCRS tool is being used to implement the modules of the RISC-V. And then we'll do the whole RISC-V design and see what size it is. It's going to be big. QDI implementation, we know it's from 2.5 to 4 times larger than an equivalent circuit produced in synchronous design. We know that. Maybe we can, if we can get to be twice the size of the synchronous implementation, we are very happy, right? I don't know if I answered that. Professor Suzanne? So what we expect is to be between 2 to 4 times the size of a synchronous implementation.
Okay, Ney, thank you very much for your talk and to answer all these questions. Thank you also to João Fragoso to be the session chair today. So thank you. Bye-bye.
Bye-bye. See you.
Bye, everyone. Thanks, Ney.